Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class as a supplement. I'm putting it online in case it would be helpful to others as well. This is the fourth video in our introductory section on derivatives. However, it's called part 2 because it has a separate second part of guided notes that you can use to follow along. If you would like access to a printable set of those notes, you can find them in the description of this video. I like to think of this last little bit of section 3.1 as just a cute little taste of something that we will study in detail in our applications of derivatives chapter. And that is the relationship between a function and its derivative graphically. I'm going to try to make this video fairly short, so let's jump right into the warm-up. I think you should pause right now and you should try this warm-up on your own and then come back to me to see the answers. I would like to highlight one thing though before you pause it, and that is this word. It says describe the direction of the graphs of each of the following functions. And by direction, I mean for each function, is it increasing, is it decreasing, or is it horizontal? Or for the ones that are curves, you can use words like turning point if you would like to. So again, I think you should pause it and then come back to me and see the answers, which are right here. Okay, let's talk about them. I have the first three uncovered for you because I think those are the easiest ones. And that's because all of the first three functions are linear, right? So looking at y equals 3x plus 5, I think we can determine fairly quickly and easily that that is a line that is increasing. It's a linear function throughout. And I hope you know why. It's because of this number right here, right? This equation is in slope-intercept form. The slope of this line is 3, and the fact that it is a positive value means that that line is increasing. Y equals negative 2x plus 1 is showing that you have a line with a slope of negative 2, and so that means that the line is decreasing. And finally, y equals 8. Be careful when you tell me what type of line that is. Sometimes I ask my students, what type of line is y equals 8? And they say straight. It's a straight line. It's a horizontal line, right? And I never write it like this except, to highlight this fact right now. If you would like to write it in full slope-intercept form, it would be y equals 0x plus 8. And so the slope being 0 shows you that it is a horizontal line. All right, so now that we have the easy ones out of the way, let's take a look at the other three, which are curves. In part D, we have y equals x squared, and here's what I said, and you might have said something slightly different, but I hope you just realize that this is a curve that is not going in one direction throughout. It is decreasing for all x less than 0, and it is increasing for all x greater than 0. I ran out of room here, but I probably could have said a little bit more. I should have said a little bit more, and that is that at x equals 0, it is a turning point, right? Or what you're going to see very shortly is that means that we have, because it's a smooth turning point, we have what's called a horizontal tangent there. So you can say that there is a place where the function is horizontal. For the next one, okay, I just sort of got a little bit lazy here. And I just said that it has an infinite amount of intervals that are increasing and decreasing, right? Because we have that sine wave and we know that it goes up, it goes down, it has all of those turning points throughout. And so, I just was sort of general there and said, we can't say one particular thing, one particular direction for that graph. It has an infinite set of intervals of increasing parts and decreasing parts. And finally, y equals e to the x. I hope you know, that this is an increasing function. It is increasing throughout, and that is something that we will discuss further as we continue to study the relationship between functions and their derivatives. What we want to start to talk about today, and again, this is just a little bit of like the beginning of the discussion on this topic, is how can we know for these curves when they're increasing and when they're decreasing? And that might not seem like it's something that's very important to answer right now, but as you'll see when we study this in chapter 4, it is going to be a very important question to be able to answer. And what you're going to find is that the way that you answer that question is with the derivative. it's actually kind of difficult to be able to look at a function and say when it's increasing and when it's decreasing if you don't know a whole lot about the function, meaning it's not like a common function. However, you can fairly quickly and easily look at the derivative, and the derivative will tell you all of that information. Okay, so let me move on to the next part. Oh, I guess this is called example 1. Where we are going to take a look at the graph of f of x equals x cubed, and then we're going to look at the graph of its derivative, and we're going to start to see the relationship here between a function and a derivative graphically. Okay, so all it says is compare the graph of the function with the graph of its derivative. So let's just do the graph of the function first, and we're just going to do like a quick sketch. We know that f of x equals x cubed is this S-shaped graph, like this. Again, I'm just doing a quick sketch. But in particular, something that I want you to notice about this function is that it is increasing throughout. So I'm just going to label here the direction of the graph. Technically, it's horizontal at x equals 0, but I'm not too concerned with that right now. We'll be able to establish that, a little bit later on fairly easily. Right now, let's just focus on for everywhere except x equals 0, it is increasing. Okay, now what we're going to do is compare that to the graph of the derivative, and I hope you remember this one from the last video. The derivative of x cubed is what? 3x squared, right? Okay, and so let's just do a sketch of what 3x squared could look like. And what you're going to see is that you can't label this graph as also increasing throughout. The function is increasing throughout, yet the derivative, hey, just so you know, in case you're not aware of this, you should be reading the direction of a graph from left to right. Meaning, if you start to the left and you move toward the right, what is that graph doing? It is decreasing until x equals 0, and then it's increasing, right? Okay, and that's not a relationship that we want to look at here, the direction of the function and the direction of the derivative. Okay, that's not what we're trying to establish. What we want to do is go back to this. How did we know that this function was increasing? Okay, this is another increasing function, just like y equals x cubed. It's just this one is a line, y equals x cubed is a curve. How do we know it's increasing? We said look at the slope, right? And what was it about the slope? It is that it was positive. Positive slope means that a line is increasing. Well, the same relationship is happening here. Notice that all of these f prime values, you can think of the y-axis as f prime of x being over here. These are f prime values over here. You're graphing x versus f prime of x. They are all above the x-axis, except at x equals 0, of course. So what we can say is, since they are all above the x-axis, that graph is above the x-axis. That means that we could say the derivative is always positive. And being able to figure out where a derivative is positive, where it's negative, where it's 0, is actually an easier question to answer than where a function is increasing, turning, or decreasing many times. And so that's why we like to establish this relationship so that we understand it early and we are able to use it when we see it again in chapter 4. Okay, so what we're going to be focusing on, just to move ahead for a moment, and then we'll go back to that 3 things to keep in mind, is we're going to be focusing on just basic matching of curves and their the graphs of their derivatives. Okay, matching, multiple choice form, and then we will start to talk about a little bit of sketching a graph of a derivative or a graph of a function, but only linearly for now. And eventually, again, in chapter 4, we'll see that sketching happen with curves. Okay, let's go back to the 3 things to keep in mind, though, and I want to tell you that what I'm going to be doing with these 3 things in mind is I'm going to be assigning a color for each of them. So I like to do a sort of color coding system to show you how to very easily match the graph of a function with the graph of its derivative. And it needs 3 colors. So if you need to pause and get 3 colors, if you think you'd like to do a color coding system as well for your notes, then go ahead and do that. Okay. The first thing to keep in mind is that when a function is increasing, the derivative is positive. So increasing function means the derivative is positive. Keep in mind, positive means above the x-axis graphically. And I'm going to assign that to be green. For part 2, let's go with red. When the function is decreasing, the derivative is negative. Again, I'm going to show that on my graphs with the color red. And finally, I'm going to use blue for number 3. When the function has a horizontal tangent, we'll talk more about that when we get there, the derivative is 0. Okay, actually, I'm going to point that out right here on f of x equals x cubed. It's kind of hard to see on this graph that there is actually a horizontal tangent at x equals 0. However, it's really easy to see that it is occurring when you look at the graph of the derivative. You know, when you look at f prime of 0, notice that you get a derivative value of 0. Right? You can see here on the graph. The graph crosses the x-axis, or it touches the x-axis at x equals 0. And so that fact right there, that the derivative value of 3x squared at x equals 0 is 0, that tells you that this is a horizontal tangent. Even though it might be hard to visualize, it might be hard to draw. You know, a lot of students don't want to draw that the tangent line here horizontal because it sort of, you know, just cuts right through the function. But we can say that right there is a horizontal tangent because the derivative value is 0. Okay, let me show you some better examples of that here in example 2. Match the graph of each function in A through D. So these are the original functions over here, with the graphs of the derivatives in Roman numerals 1 through 4. So these are the derivative graphs. Give reasons for your choices. Okay, well, we're not going to write out reasons, but we're just going to color code to show our reasoning. Okay, so what I'm going to do is grab, you know, my first color, which was assigned to when a function is increasing, the derivative is positive. And I'm just going to color code to show you what I'm looking at here and how these graphs match. In A, I can see that from this point to this peak right here, that part of my function is increasing. So what I'm looking for over here to match the graph of the derivative is where do I have a graph that in this specific interval, it is above the x-axis, it's positive. Okay, also, I'm going to do a little bit more highlighting with this graph before I tell you which one matches. I can see that there is a decreasing section here and a decreasing section here. I'm making it look linear and it's not, I'm sorry. Okay, decreasing interval means that I should have 2 intervals in the same place, the same intervals here and here that are below the x-axis, that are negative on the graph of the derivative. And finally, I'm going to grab my blue color. I see that there is a turning point, which I can establish as a horizontal tangent. Like if I drew a tangent line at that point, it would be horizontal here, and there is another one up here. Right? The tangent line would be horizontal there. And that means, okay, this is one where students finally, it kind of clicks. They go, oh, the graph of the derivative should have 2 0 points. It should have 2 places where it crosses the x-axis. Okay, so now looking at your options, can you see that Roman numeral number 2 has those 2 zeros? It has the 2 places where it crosses the x-axis. It has a negative interval here and a negative interval here. I mean negative because it's below the x-axis. and it has a positive interval here. And so these graphs match. This is the graph of the function. This is the graph of its derivative, right? And so I'm going to go down here. Oh my gosh, I need to go away. There we go. Okay. Still here. You just can't see me. We're going to go down here to A and say that it matches with Roman numeral 2. Okay. All right, let's keep going. And I'm actually going to go a little bit out of order here just to, I think just in the interest of what makes most sense. So I'm going to grab my green again. Remember, my green color was for when the function is increasing, the derivative is positive. So let's jump down to part D. Let's take a look at that one. Again, when you're looking at a graph of an original function, what you want to be looking at is the direction of the graph. So left to right. Left to right, this graph is increasing. Watch this. I'll go back and forth. Decreasing. Increasing. Decreasing. Are we okay with that? Going up, going down, going up, going down. Because of the change in direction, we have 1, 2, 3 turning points, 3 horizontal tangents. And so now I'm going over here and I'm looking for, something that matches up with that in terms of the derivative. Now, going back one more time, remember when the function is increasing, the derivative is positive above the x-axis. When the function is decreasing, the derivative is negative below the x-axis. When the function has those horizontal tangents, the derivative is 0. So can you match it up? I hope you're saying 3. Oh my gosh, it's 3, right? There is, first of all, 1, 2, 3 places where it crosses the x-axis, making a derivative value of 0. It is above the x-axis in this interval, and it's above the x-axis in this interval. Yes, this whole thing. Okay, color code that whole little hump there as green. That matches up with this over here, increasing, positive. Okay, it has a negative part here, which matches up with this decreasing section, and a negative part here. And so we can say that D matches with Roman numeral 3. I hope at this point you're sort of getting the hang of this and you're going, oh, okay, it kind of makes sense. Whenever we do this in class, I absolutely love it. I feel like Bob Ross, and all of my students are just calmly color coding everything. And it's just like quiet, other than like the dropping of like colored pencils to pick up another color. It's just a nice experience. I suggest you try it sometime. All right, try teaching a lesson like this to a group of students and see how you will feel like Bob Ross and you will feel very calm. All right, let's take a look at C. So again, whenever I'm looking at an original function, we're looking at when is it, like the direction of it. When is it increasing? When is it decreasing? When is it turning? So I see an interval that is decreasing to here. It then changes direction and it is increasing. And it has a turning point right here at x equals 0. So I'm hoping that you're looking at Roman numeral 1. That makes sense, right? There's that 0 point. Derivative is 0 because we have a horizontal tangent right here. We have a section that is below the x-axis before x equals 0, and then we have a section that is above the x-axis after x equals 0. So those match nicely. Part C, or graph C, goes with derivative graph 1. And finally, by process of elimination, that means graph B matches up with Roman numeral 4. Let's talk about why. There's something pretty important that we need to discuss, and we're going to just briefly touch on it right now, and then we will discuss it in detail in the next section. The next section is all about differentiability. That's a weird word, right? Differentiability means when a derivative can be taken. I think that's a good definition. We'll go with it. And what you're going to find out very quickly, meaning right here, is that there are some times when we say a derivative does not exist. Okay, let me do a little bit of color coding. I see that my function here is increasing, and then it is decreasing, and then it's increasing again. And so I'm looking for positive, then negative, then positive. I see all of that right here very nicely, right? Positive, then negative, then positive. Another reason that this one definitely makes sense is that this is a piecewise linear function, right? It's made up of 3 pieces that are all lines. And so the derivative should be made up of piecewise constant functions. Does that make sense? Constant slope in this interval, different constant slope in this interval, constant slope in this interval. And that's what you see here. One thing that I want to point out, we're not going to color code it with anything, we're just going to talk about it right now, is the fact that at these turning points, okay, these were all nice smooth turning points, and we talked about those being zeros on the derivative. At these sharp turning points, that's actually what you can call them, sharp turning points, what you see in the derivative are discontinuities. Okay, and that means that sharp turning points are a place where the derivative does not exist. Now, that is something that we will discuss in detail, as I said, in the next section. It has to do with the fact that a derivative is a limit. We need to discuss that thoroughly. I don't want to do that in this video. I just want you to be aware that it happens. Sharp turning points are where if a sharp turning point you can say is not differentiable. Okay, that's another sort of word that you're going to need to know. And again, that means that your derivative doesn't exist or has a discontinuity there. Okay, so in this next part, we're into a U-try where we're doing the same thing. The directions say match the graph of each function in 1 through 4 with the graph of its derivative in A through D. Give reasons for your choices. Again, you don't have to write out reasons if you don't want to. You could just do some color coding. At this point, sometimes I have students say, I totally understand this. Do I have to color code? Because I get it. And I say, no, not really, but I like it. I think it's pretty and I think it's helpful. And for students who struggle with this concept of how do we do this matching, use the color coding system. Remember that over here, these are the original functions. You are color coding the direction of the graph. Increasing would be one color. Decreasing would be a different color. Turning points would be a third color. Yet when you get over here to the derivative, you are not looking at the direction. You're looking at the sign. Where is it above the x-axis? Where is it below the x-axis? Where does it cross the x-axis? Okay, as usual, I think you should pause the video right now. I'm going to come back to you here. I think you should pause the video. I'm going to pause the video as well. I'm going to fill in the answers and then we'll talk about them briefly. Okay, I'm back. Here's the answers. 1 is B, 2 is A, 3 is D, 4 is C. And as I said before, I think, a lot of students at this point might be able to say, well, I couldn't definitely do this process with the process of matching without the color coding system. But I do think that you should at least look and see, does the color coding system make sense? Because I have found that at times my students can correctly match, but they're not giving good reasons for why they're matching a graph of a function with the graph of the derivative. So for example, take a look at number 1. The function in number 1 is increasing, decreasing, increasing, 2 turning points, 2 horizontal tangent points. That matches up with B. Because of this, look at my color coding. The derivative graph is positive, then negative, then positive, and 2 0 points, 2 places where the derivative equals 0. So, make sure that that makes sense, because eventually you will have to describe it. You'll have to explain why, why they match. And you can't say, well, this one's increasing here and this one's increasing there. No, that's not it. Increasing function matches with positive derivative. Decreasing function matches with negative derivative. Horizontal tangents match with zeros on the derivative. Okay, so same idea for number 2. I also have students say things like, well, I already know some of the derivative rules. So I know if this is something like y equals x squared, the derivative is y equals 2x, which is linear, and so I know that they match for that reason. I would still go back to direction matching with sign, okay, because it's going to be important in the applications chapter. So a decreasing function matches with a negative derivative, a turning point matches with a 0, an increasing function matches with a positive derivative. One other thing I want to mention is for number 3, this is another place where you see a point that we are going to say is not differentiable. I'm just going to write those words off to the side so that you can see them, because pretty quickly this is going to become very important. The word differentiable. Not differentiable means the derivative doesn't exist, and as I said in example 2, that's going to happen at, instead of a smooth turning point, a sharp turning point. And x equals 0 in number 3 is actually another example of a sharp turning point. Even though it's made up of a turning of curves, not lines, we still call this a sharp turning point, and we will explore that more in the next section. Right now, I just want you to know that at x equals 0, what you're looking at for this function is a discontinuity that is in the form of a vertical asymptote, right, or an infinite discontinuity. And we'll talk a lot more about that as we keep going. Finally, 4 matches up with C. You could just basically say I see 3 turning points and 3 zeros. Or, you can match up all of the increasing parts with positive parts, decreasing parts with negative parts. Yay. I hope that was fun. I always have fun with those. It's just a cool thing to see how they relate. The intervals are all relatable. What is happening on a function, you can relate to something that's happening on the derivative. And I don't know, I just think that's a pretty cool thing to notice. All right, moving on to example 3. This should be a nice, quick, and easy one. However, you need to be careful of one little thing. This is multiple choice now. Given the graph of the derivative, choose the graph of the function f of x. Okay, the one thing that you need to notice is in the directions. It's kind of here, but I'm sorry, this is really blurry, I know. It says given the graph of the derivative, meaning over here, what you're seeing to the left is the graph of the derivative. So it's sort of backwards, we're looking at the derivative first, and then we're trying to pick out what would be the original function. So with that being said, I'm going to tell you right away, the answer is not A, okay? If this was the original function, and we were looking for the graph of the derivative, yes, A could be it, okay? But what we're looking at here is the fact that this derivative interval is positive. These intervals, on the derivative are negative, right? That's what you're looking at when you're looking at the graph of a derivative. You're looking for the sign. And I see 2 zeros. Okay, so it's just sort of backwards. You're at the derivative, you need to look at the function. So what I'm looking for here is a place where the function is decreasing, turns to increasing, turns to decreasing. Okay, did you hear me? Decreasing, turns to increasing, turns to decreasing. Ugh, this is just another moment where I'm like, I wish I was with you guys in the classroom right now, because I like to just have my students look at it and signal to me the answer. I say, if you think it's A, hold up a 1. If you think it's B, hold up a 2. If you think it's C, hold up a 3. And I love to see everybody just holding up a 2. They're like, yeah, it's B. Easy peasy, right? At least for now. All right, finally, the last part here is where we're going to start to do some sketching. In this first example, we're going to look at, given a graph of a function, can we sketch the graph of the derivative? And then we'll turn it around in the last part where we say, if we have the graph of the derivative, can we sketch the graph of the original function? We're only going to do this right now with linear graphs because they're the easiest place to start. And then eventually in chapter 4, we will do what's called curve sketching. Okay, but again, let's just enjoy the easy right now. Okay, so what you need to keep in mind is that what you're looking at here, I'm trying to pick a color. Let's go back to purple. What you're looking at here is the graph of the function. Notice it says y equals f of x. In the directions, it says the graph of the function y equals f of x shown here is made of line segments joined end to end. What we're asked to do is graph the function's derivative. You can see over here y prime equals f prime of x. And then identify values of x for which the function is, notice that wording that I talked about earlier, not differentiable. All right, well, actually, I kind of think we should do the not differentiable part first, because that's going to tell us something about how we draw points on our derivative graph. Where is this function not differentiable? It's not differentiable at all of those sharp turning points, or what we're going to look at here is any place where the slope makes a quick change. Okay, meaning here I'm doing a slope of up 2 over 1, and then very quickly at x equals 0, I change to a slope of 0. Okay, I'm going to write this in because it's actually really important for us to know these specific slopes. On the interval from -1 to 0, I am looking at a slope of 2, but then very quickly at x equals 0, I change to a slope of 0, right? Because it's horizontal here. And so x equals 0 is going to be a place where it's not differentiable. So let's just establish all of those places where that happens. X equals 1 is another place, right? It changes from a 0 slope to a steeper decreasing slope, we'll just say for now. And so x equals 1 is another place where it's not differentiable. X equals 2 is a place where it's not differentiable, even though it seems like it's not a sharp turning point or not a sharp change. It is a change from one constant slope to another constant slope. And so we are going to say x equals 2 is a place where it's not differentiable. And finally, at x equals 3, it is one more place where it's changing from one constant slope to another constant slope, and that is another place where it's not differentiable. Now let's finish off this graph by just talking about what are the slopes everywhere. We have a slope of down 2 over 1, down 2 right 1, which we can call a slope of -2. That looks weird. I'm going to try to do that better. M equals -2. And then here, from x equals 2 to x equals 3, we're looking at a slope of down 1, right 1, which is a -1 slope. And finally, here we're looking at a slope of 0. Okay, those slope values are the derivative values on the given intervals for your graph. Okay, meaning if I am looking at a slope of 2, that means the derivative everywhere from -1 to 0 is a slope of 2. Constant slope. See how I'm drawing a horizontal line? Now, in particular, at x equals 0, we said that that's one place that it is not differentiable. So what I want you to do at that ending point is put a hole. That's supposed to be an open point there. It's kind of hard to see. And then I jump to a slope of 0, meaning from 0 to 1, I'm going to go down here to a derivative value of 0. Remember, this y-axis is actually your derivative axis here. And again, since it's not differentiable at x equals 0, I put a hole there. I say it is a constant slope of 0 until x equals 1. X equals 1 is also a place where it's not differentiable, so put a hole there as well. Okay, now I'm going to jump down to a slope of -2. Start with a hole because x equals 1 is not differentiable. Constant slope of -2 from x equals 1 to x equals 2, and then put another hole because, again, x equals 2 is a place where it's not differentiable, so you don't want to have a closed point there. Jump up to a slope of -1 on the interval from 2 to 3. And again, put a hole here and a hole here because it is not differentiable, meaning the derivative does not exist at x equals 2 and x equals 3. And finally, jump up to a horizontal line from 3 to 4 at y prime equals 0. You can put a hole at x equals 3. 4 is an endpoint, so we do typically say that we're just going to end with a closed point there at the endpoints. And there you have it. That is how you draw the graph of a derivative from the graph of a function. You look at the slope at every point on the given interval. Okay, luckily for us, the slope was constant for these 1, 2, 3, 4, 5 intervals, which means we could just draw horizontal lines on those intervals. Okay, and again, that's what we're going to stick to for right now, and we'll discuss how to do this sort of thing with curves much later on. Finally, example 5, we are going to do the same sort of thing we just did, only backwards. It says sketch the graph of y equals f of x over the closed interval from -7 to 7, given the following properties of the function. First property, the graph of f of x is made of line segments joined end to end. Second thing, the graph of f of x starts at the point -7, -7. Okay, this can get confusing sometimes. You see a -7, 7 here. That's the given x interval, meaning you're going to go from here to here along the x-axis. This point, -7, -7, which is way down here, that's your starting point. And finally, 3, the graph of f of x is the step function shown below. So this graph is the derivative. Okay, and so what we see are horizontal line segments for the derivative graph, and that's going to translate to lines of constant slope for our function. I already have my starting point. What I need to do now is I need to establish what's the slope from that starting point and for what interval am I drawing that slope. So I'm looking at a derivative value, y prime value. We should label this y prime. That might help. Y prime value of 2 on the interval from -7 all the way to 0. So from -7 all the way to 0, I'm going to be drawing a line that has a slope of 2. M equals 2. And so how do you draw a line that has a slope of 2? You go up to right 1, right? Up to right 1. You could skip some if you want to. You can go up 4, right 2. I'd be careful. And if you do it correctly, you should be drawing a line that ends at the point 0, +7. Oh, it's so bad. I'm not even messing around today. I'm just gonna go here. I'm gonna do this. Ta-da, look at that. Cute. All right. Back to drawing points, then I'll draw a line. Now, what I'm going to have here, notice I ended with a closed point. That's because I see right here it says closed line segments joined end to end. Okay, just because there's holes in the derivative doesn't mean there's holes in the function. The holes in the derivative indicate the sharp turns. Like we're about to have a sharp turn. It's going to be a line segment from x equals 0 to x equals 2 that has a slope of -4. So watch this. From this point, down 4 over 1. And do it one more time. Down 4, 1, 2, 3, 4 over 1. Why does that feel weird to me? Because I didn't go down 4, right? 1, 2, 3. Yep, that's my problem. Like something feels off. Okay, let's try that again. Down 4 over 1. Down 4 over 1. And I'm going to stop there because that's where the interval here ends at x equals 2. And then again, I'm going to draw a line to connect those points. Back to the pen, we have 2 more line segments to draw. The next one, at x equals 2, we will be drawing a line segment that has a slope of 1, right? I should probably write here y prime equals -4. Now we're up at y prime equals 1. Right, we're at 1. So from x equals 2 to x equals 5, we will go up 1, right 1. Up 1, right 1, up 1, right 1. And draw that line. I want to do color. Okay. And finally, what do we end with? From x equals 5 to x equals 7, we end with a horizontal line, right? I didn't really need to draw on those points, did I? And we're ending with a horizontal line segment because the y prime value on this interval is 0. Yay! Okay, so again, this is just a little taste of relating graphs of functions with graphs of derivatives or vice versa. And as usual, I hope it was helpful. See you again soon. Bye.